So section 4.7, the title of it is on page 205, and it's called Transformations of Polynomial Functions. Does the word transformations bring back any memories for you?
Right.
Well, moving things around, squashing things, stretching things, reflecting them,
Yeah.
right? Let me remind you in general, just to bring it back to your conscious memory about these transformations in a general way. Then we'll make it specific to a couple of graphs. It says transformations of polynomial functions. It's really just transformations of squared functions, cubed functions, and fourth degree functions. That's all we're going to deal with. Okay? But anyway, these are the generalized transformations. If the function that we are considering changing, moving around, whatever, what does this do to the original function?
Move it 3 to the right.
Alexis thinks it moves it 3 to the right.
Yeah.
Okay? What does this do to the original function?
Down 4.
Good. Is everybody clear? Everybody happy with that? Okay. What does this do?
Reflection in the y.
Good man. Reflection in the y, because it happens inside. It's a horizontal reflection, because it's inside. This was a horizontal move to the right. So what does this do? Yeah, reflects it this way, because the changing part of it right out here is on the outside of the function, and that's on the outside is always a vertical thing, like this. Moved it down vertically forward because it was on the outside of the function, where this moved it right because it was on the inside. What does this do to it?
Vertical stretch 3.
Vertical stretch 3, do you agree? Because it's on the outside? So what does this do? Careful now. Horizontal, because it's inside. Horizontal what?
Shrink.
Shrink of?
No,
1/3.
1/3.
Wait.
Because it's inside, you must think opposite. Since this is a multiplier, the opposite of multiplying is dividing. It's a reciprocal. Here, you think opposite, but it was not a multiplier, it was a subtractor, so you think add. When it's multiplying, you think reciprocal instead, because the opposite of multiplying is dividing, which is tipping things over in a division problem. Okay, so what does this do? I'll put it up here. What does this one do? F of 2/3.
It's a horizontal stretch of
3 over 2.
3 over 2, 3/2, same thing. Both said the same way. Inside means horizontal. Tip it over. 3/2 is bigger than 1, so it's a stretch. Horizontal stretch. It's like somebody grabbed the thing and went like this with it. We clear on that? And so what does this do? Let's see if you can get several together. What would something like this do?
So
Give me one of the things that happens, that does to that.
it goes up 1.
Goes up 1. I like that one. That's good. That's easy to see. What?
Reflection in the x-axis.
Reflection in the x, because that's on the outside. Right 2, and
Up 1.
we already said the up one. One more.
and a vertical shrink.
Shrink of 3/4. A shrink is 3/4 is less than 1. Happens on the outside. We take it as is, and it's smaller than 1. Do you recall? Okay, that's what we're going to be doing to polynomial functions. It's not hard because you've done it before. You're familiar with this. I didn't have to reteach it. We just had to relearn it. We just had to bring it to our conscious memory. So I'm going to erase this, and then I'm going to talk to you about what shape these parent functions have that we're going to be dealing with. You already know what this looks like, right? If you have f of x equals the parent function x squared, y'all got a good image in your mind what that looks like?
Yeah.
Do you have a good image in your mind how to graph it accurately? Yeah. Start at the origin. Out 1, up 1, out 1, up 3, out 1, up 5, out 1, up 7 if you want, right? Remember that? And then get the symmetry points on the other side, gives you a nice parabola. Okay, so we can transform this by transforming this side according to those things I just erased. Will affect this, and we can tell how it's going to affect it. Do you know what this graph looks like? You may or may not. Do you have an idea in your mind what that thing looks like?
I think it
Times everything by 3.
This makes it big.
No, it's a cube. It's not a multiplier of 3, it's a cuber. Kind of. It's a little bit, it's,
Does it go out 1, over 1, out 1,
Let's-
over 8?
yeah, it does. Let's take a look at this. Let's look at some points. First of all, well, let's do this. -3, -2, -1, 0, 1, 2, 3. Those are always a good place to start. Sometimes you want to amend that, but I'm going to start with those for X choices. If I plug -3 into this, what Y value will come out of it?
Negative.
Good.
Awesome.
It'll be negative because it's an odd power, so it's 3 negative signs. -27, what will come out if I put that in?
-8,
Good. And this one?
-1,
Good.
0,
1.
8, 27.
Does it make sense to you that this one and this one are not something I want to count because I'm not tall enough and I don't want to count that far?
Yeah.
So I'm not going to consider those. Maybe I can get a decent shape just with what's left, and I think I can. The 8's not too big, but that 27 got big in a hurry, so I'm not going to count with that one. So I'm going to plot these points, and I'm going to start, if it's okay with you, even though it's not the starting one, I'm going to start with 0, 0. And then I'm going to consider the positive ones, and I'll see how those negative ones are like them or not. They look like they're the same kinds of numbers, but so I'm going to go out 1, up 1. And then when I get to 2, I'm going to start at the origin, 1, 2, and I have to go 8. If I also take the negative ones going back, so I got the -1 as a point right here, and then I go back to -2 right here and down 8, my graph looks like this. It bends pretty hard there and then goes almost straight down, because I remember the next thing I want to hit over here at -3 would be 27, way down there, so it's pretty vertical. And right here goes up to that, and whoops, it's not that vertical, but it's close. And for those people that are viewing this, they can't see. Sorry, everybody, you have to imagine that I just graphed that. So what we did is we plotted the origin, we plotted 1, 1, and -1, -1. That was these guys right here, and they appear to be kind of aligned, except for when we drew these, that made the curve. So we went out 2, down -8, and we went to the right 2 and up 8, and we get this. Feels like it's kind of doing the same thing in this quadrant as it does this one, right? But it's not really symmetrical because it doesn't reflect over the x-axis or the y-axis, or the x-axis or the y, but it is what we call origin symmetry. It does kind of the same thing in the third quadrant that it does in the first and goes through the origin. It's called origin symmetry. Anyway, that's your general shape for the cube function. And the fact that we've got both sets of 1s and 2s and 8s, that's enough to give you a shape. What would happen if I vertically stretched that by 2? You'd go out 1, up 2. And then out 1 more and up 16. That's still a big count. But that's how it's going to be affected just like that, and you would come back the same way. Okay, does anybody know what the graph of this looks like?
You go out 1, out 1.
Shall we get some points and see?
Yeah.
Okay. X and Y. I don't think I'm going to use those 3's again because they were too big with a 3. They're going to be even bigger with a 4th power. So I'm just going to go -2, -1, 0, 1, 2, and see what I get. What happens when I put a 2 in here? A -2.
You get 16, right?
16, yeah. And it's positive because there's 4 negatives. This one? 1. This one?
0,
1 and
16.
That's a little extreme for counting, but I don't have much else. I can't just use these 3 points because then it will look like a V. So I'm going to have to count them out once just to take a look at it. So let's try graphing those points. Starting at the origin again, I'm going to go out to the right and I'll come back to the back, or come back to the left. So I go out 1, up 1. It seems like that's always the case because when you power 1, you get 1. And then you go out 2 and up 16. Oh, really? 16. Symmetry points because -1, 1 is also a point, and so is -2, 16. And so it appears to be a really skinny parabola, right? Except right in here, something weird happens, and I didn't plot any points here. To do this, rather than actually plot them here for you, because it looks like a really skinny parabola, it is not. but it resembles it a lot. But it's not a parabola. I want you to see the differences, and the differences happen right near the origin. What I mean by differences, I mean the difference between x squared, which you're familiar with, and x to the fourth, which appears to be an awful lot like it. There are subtle differences, and they occur in here. Take a look. If we go to the grapher and go to y equals, I want to compare x squared, and I want to do x to the fourth. But I want a window that really pinches down on this area here, because I want you to see the differences close to the origin. So I'm going to let x go from -2 to 2 by 1s. And I'm going to let the y's go from -1 to 2, because I want focus right in here. So -1 to 2 would focus that area right there by 1s. All right, so we're going to graph this. First one is x squared, which is what you expect. And here comes x to the fourth. See? They both share that point, 1, 1, -1, 1, like we saw on the graph. But right in here, the fourth power, which is this guy right here, is flatter. And really and truly, based on what you know about polynomials, if you had thought about it, you should expect that. Because this one right here, if we let it equal 0, oops. Try that, Ms. J, come on. And that means that you have x times x times x times x equals 0. Each one of these gets their shot at being 0, and they're all 0. But it's multiplicity 4, which means when it encounters 0 on the x-axis, not only will it bounce off, it will flatten out, because that's a higher odd number than, or a higher even number than 2. The bigger the even number, the flatter it gets as it goes up. Just to show you that, let's look at x to the 6th in this window. Okay, watch it coming in with the others. Here comes. See how it flattens out just a little bit more? It appears to ride along the x-axis. It doesn't actually. It only crosses it right here. It just stays closer to the x-axis longer. Let's do something really extreme, like let's erase x to the 6th. Let's clear that one and do x to the
32nd.
Okay, we can do that. X raised to the 32nd. It has to be even. Now watch what happens. There's your parabola. Comes the fourth power. There comes the 32. Look how long it appears to ride along the x-axis. You got to understand, though, it doesn't actually run along the x-axis straight like this and then take off. It just stays closer to the x-axis longer. It only hits it right here. That's the only 0 it has. But it's so close to the x-axis, you can't tell the difference when you go to draw it. Okay, you with me there? So we should expect a 4th degree polynomial to flatten out near the origin down here. So while a parabola comes up like this, that one will come down and will come down sharper from there, and it will appear to ride along the x a little bit more as it goes up. Just got a flatter bottom. Kind of like when people get older, they tend to spread. That's what they say. Okay. All right. So would you look then, now that you kind of get a feel for what these 3 functions look like. This one it starts in the 3rd quadrant and goes up like that. And this one looks just like a parabola and is flatter at the bottom. Okay, here we go. Look at example 1 on page 206. And it says, describe the transformation of f of x equals x cubed, so our parent function is x cubed, represented by x plus 5 cubed plus 2. So I'm going to erase this stuff up here now that you got kind of an idea what things are going to look like. Our parent function is x cubed. How are we going to transform, or how are we going to show the transformation of this? Knowing what x cubed looks like, it's going to be x plus 5 cubed plus, what was it, 2?
Yeah.
What's it going to do to the parent? Just tell me about the moves, and then we'll see how we can graph it. Left 5. Up 2. And where was, here's what I mean. This is what it looked like before, if you'll recall, a cubed function. It started with these 1s here, and then it had these 8s down here somewhere. So it's going to drop off like that. What I'm suggesting is that if you could grab this thing, you should grab it right here where it turns. And move that thingy left 5. 1, 2, 3, 4, 5, and up 2. And pretend that this is your new origin. Because that's what happened. The 0, 0 point became negative 5, 2. So we plot a point here, and here, and here, and then down 8, and go out 1 and down 8 from there. And up 8, go out 1 more, go up 8 here. So what we've really done is just kind of move the origin, and so it goes here. It's not very hard to graph if you understand your representative points on the original. You know what I'm saying? Okay. So that one wasn't that hard. That was a move left and up. That's not very hard to move it if it stays rigid. What you should move is this turning point right here. Just pick it up and move it where it goes, put it there, and then pretend that's your new origin and plot just like you did here when it was at the origin. If you're just moving. All right, take a look at example 2. It says, describe the transformation of f represented by g, and then graph it. So now we're given a parent function and a transformed function, and we have to describe with words, kind of like we did right here without really needing to. We just wanted to know where we were going. We're going to describe what's going on. So in a part, we're transforming x to the 4th, and the new function is negative 1/4 x to the 4th. That's got 2 things going on. What are they?
Reflection and shrink.
A reflection over the x, and a, what kind of shrink? A vertical shrink of a 4th, because the 1/4 happened before the 4th powering happened. So you got to tip that thing over and make it wider, because a vertical shrink squashes it, making it thicker. And so when it says, and graph it, I think they want you to graph the parent and also and when you do this, folks, I don't care that you give me exact points, but if you wanted exact points, here's a really quick way to do it. So your 4th power looks like this, has 0, 0, it has a 1, 1, and it's got a 2, 16. So it's really, and it rides along the bottom a little bit like that. So this one's a little bit flatter before it goes up like that. Just kind of make it flat if you can do it by hand. And the other one's going to what? Flip over? Yeah. And be wider because it got vertically shrunk. So we still start in the same place. It hasn't gone anywhere. It just flipped over, and it's wider now. So it rides a little longer there before it drops off, and we make it wider. This would be good enough for me. It's fine that way. But if you want to know just how much wider, here's what you do. This is really cool about your calculator. Watch this. What you can do to graph points accurately without having to plug it in, try to figure out what's coming out of there, you can, since we want to just, we know how this one's graphing, the blue one. I just want to graph the red one. I'm going to actually put that in there, negative. Instead of 1/4, I'm going to put 0.25 so it's easier to type. X raised to the 4th. And if I want to get some points of accuracy, I think I'm going to have to change my window, let my y's go a little farther down. You can look at that and go, well, that doesn't help me plot any points. Well, this does. Remember the table? Remember your table? So I'm going to go second table set. That's just above your window. I'm going to do a table set. And we're going to start the x's at -3. That'll be fine. And we're going to increment by 1s because we don't want to be graphing half points and stuff. And then go second table. I don't want to plot that. It's too hard to count. But I could plot this. -2, -4. So instead of just a quickly drawn thing like this, we could go -2, -4. I can plot that. I've also got a -1 and just down 1/4. That would be, allows it to ride along the top, 0, 0, and then some symmetry points. And that would be enough to make it show just how much wider it is with that 1/4. It's not as wide as I made it before. Some way or another, you need to indicate that the thing got wider and also tipped over. Okay, so you can get points of accuracy by using your table here. When you go to graph, look at the B part. This one is x to the 5th. I told you we were only going to go up to x to the 4th. X to the 5th is like unto x cubed, right? Except for right here when it turns, just like the x to the 4th was like x squared. It'll be like x cubed, except for right here where it turns, it will appear to ride a little longer before it drops off, just like the 1/4 one, flattened out at the critical value. You know what I'm saying? That's the only difference. And what it says, we're going to transform it to parenthesis 2x raised to the fifth minus 3. Can you describe those transformations? 2x all to the fifth, and with our parent function's x to the fifth, minus 3. Can you describe them? How this is transformed from the parent? Horizontal shrink, 1/2, that's good. That's this guy right here. And down 3. So if this is kinda, sorta what the fifth degree, or yeah, the parent function for fifth goes, I'm gonna come down 3. And that's where my little anchor point's gonna be right here. It didn't get reflected over anything, it's just shrunk. And horizontally shrunk means squeezed in. So give it this same shape, but make it skinnier. And that will be enough. It's been horizontally brought together like that, so it's got to be skinnier than the blue one, whatever its value is. You want to graph it a little more perfectly, then put that function in there and get yourself some points to plot with your table. It's not very hard. Example 3, ooh, gross, look what we got going on now. It's not just x cubed, or x to the fifth, or x squared. It is a cubed function, but there's other junk with it. This is where your table, this thingy, the table thing, aspect of this is going to be really, really important after you have written the proper transformation. So this is going to get a little tougher here than what you've seen so far. Because instead of giving you a transform function, they're going to make you transform the function they gave you, and it's not apparent. So watch how this works. The function we are to transform is x cubed plus x squared plus 1. Did I get all the signs right?
Yep.
Are they all plus? Okay. So that's it's not our parent, but that's the one we intend to transform. And it says, write a rule for g and then graph each function. Describe the graph of g as a transformation of the graph of f. Wow. So they want us to take g, they want us to create a g function that is f of negative x. So that's the first thing I'm going to write down is a generalized idea. The g, the one we're going to try to write, is going to be related to this one in this way. It's going to be f of negative x. Without looking at this or trying to figure out what the graph is going to be, how will g be different from f if I make g this transformation? What's going to happen?
Reflection.
Over the y-axis because it's inside. That's what's going to happen to it. Whatever this thing looks like, we are going to flip it over the y to make this one. But how do we write it? Well, got to remember your notation here. If we're going to rewrite g so that it is specific to f, it means that all of the x's that are in f, no matter where they occur, no matter how many there are, every one of these x's is going to become negative x because whatever's in these parentheses replaces the x in the original. Does that make sense? So it's g at the outset is going to be negative x cubed plus negative x squared plus 1 because we're replacing all the x's with what's been now put in the parentheses. Do you see that? Yes, no? Everybody lost? Okay. I thought you were saying, yes, you're lost. But you're okay. Okay. All right. Then we have to evaluate that or clean that up. What is a negative raised to the third? Negative or positive? Negative times negative times negative is?
Negative.
Negative. And x cubed is just x cubed. So it appears that we just eliminated the parentheses. That's not what happened. We cubed the negative and got a negative. We cubed the x and we got x cubed. What happens when I square this one? What will happen? It'll be plus x squared. And then plus 1. So this one kept his sign. This one didn't. So it's not quite as easy to predict quite what's going to happen. But let's take a look. Go to y equals. I'm going to graph both. I'm going to plot both these. I want to show you another cool thing about your calculator here and what it can do with 2 functions at a time. We're going to have the original, which is not apparent. It's going to be x raised to the third plus x squared plus 1. That's our original that we want to compare it to. And the second one's going to be, now we all got it all cleaned up, negative x cubed plus x squared plus 1 Gonna graph both of those together. I'm thinking the screen I've got might be big enough. I'll go to a standard screen, just so we can see it. Here's the first one. Comes the second one. Exactly what we thought, reflected over the y. Now, if you wanted to plot those, since neither one of them are parent functions, you want to plot them accurately and carefully. Here's what you can do. You can go second, table, and it will give you these x's, but those x's belong to both of these y's. So you can plot these for your original function, and these for your other function, and they'll all be in the same screen for you. That's pretty cool. This is the y values for y1. This is the y values for y2. This is the y values for the original function. These are the y values for g that we transformed. So the answer to the question is going to be these graphs. You know what this looks like? It looks like a parabola here and a parabola here, but it's not, because this whole thing's black and white. It drives me crazy. This was the first one. It came up and went around and up. This one came down, went across right here and came down. So these are not parabolas that are kissing each other there at the vertex. These are fifth degree or third degree polynomials. This would be the answer that you would write for the function. This would be the graph that you would create for the graph part of it. Do y'all see how that goes? And you can accurately create a graph with points if you need to by using your calculator and the table function. The next one is not quite so obvious. This is still f. This is the b part of this example. This is still the function f. And this time they want us to create a g function that is 3 f of x. What's that going to do to it?
Stretch it.
It's going to stretch it. Not only is it going to stretch it, it may move it up some too. As it stretches it, as it pulls it up, it's going to move the, because this right here is going to become a 3. So it was up 1 before, it'll be up 3 in the transformation. This transformation isn't nearly as obvious. But to describe the transformation, you would say vertical stretch of 3. To create the function g, you take 3. Okay, careful now and pay attention. You take that 3 times all of f, all of it, which means this. That's what it means. 3 times all of f means you got to distribute it clear through, which is 3x cubed plus 3x squared plus 3. See how that thing was, this thing was up 1 before, this is up 3? It's going to not only stretch it, it's going to move it up. So take a look at the graph that they have for you there in the B part, bottom right-hand corner of 207. If you want to duplicate that graph, you have to first write this based on the algebra that's involved. And then you got to put this in y1 and this in y2. Go to your table, plot a few points, because it's not nearly as obvious what's going to happen on this one. So I'm going to leave that f function there, and I'm going to type this one in now that I got it distributed. I graph that on a standard screen. Here's the original. There's the transformed one, and you're looking at that going, I have no idea where those points are or what happened to it. So go to your table. These are points for y1, and these are points for y2. Obviously, some of them are way too big to count. But if you can get a few of these countable ones in there and connect them, you can get the two graphs and what they compare. It will look like this. Y'all see it? Okay. So that transformation wasn't nearly as obvious. Okay, look at example 4. We've got 2 more examples to go. Hang in there. We've got plenty of time. Example 4 says, now let the graph of g be a vertical stretch by a factor of 2, followed by a translation 3 units up of the graph of f. And again, we don't have a parent function. So now they're not telling you what to change it by writing this. You have to take the words and write this part yourself. They're not handing it to you as a function transformation. They're giving you words, and you have to write the transformation and then cause the effect to happen. So this is a little tougher. It keeps getting tougher and tougher as we go along here. Thank goodness there's only 2 examples left. The function we wish to transform is x to the 4th minus 2x squared. And g of x has to be f of x with these described transformations that we've got to put in appropriately. It says, let the graph of g be a vertical stretch by a factor of 2. I'm not doing it to this yet. I'm only doing it as a generalized transformation of f. Do you see what I did there? Vertical stretch of 2. Okay. Followed by a translation 3 units up. So we had to take the words and write the transformations with respect to f. In the previous example, they gave you this part. You just had to make the algebra happen. In this one, you have to write the transformation from words and then make it happen algebraically. Here's how it's going to happen. Watch this. G of x is going to be 2 times all of f and then add 3. Did you catch that? 2 times all of f. There's all of f. 2 times all of f is a distribution. And then after you've taken 2 times all of f, you add 3 to the result. You see what's going on? Now we do that by distribution. And this is G. And if you want to know how they compare graphically, you would graph this and this in the same screen. Go to your table and plot some points if you need to. But you've got to write this transformation generally based on the words, and then apply those transformations to f, whatever it is. Finally kick out a simplified polynomial called g. Then you can put this in this new calculator, plot some points. Are we okay? You want to see that one? What the transform graph looks like or not? It's a vertical stretch, which means it's been made skinnier. And the whole thing's been made skinnier and then moved up 3. From whatever that thing looked like, which is not very easy to tell either. But you can put them both in your calculator and see what happens. Okay, last thing. Example 5. I personally find it to be very, very cool. Most people don't, but I do. And if you don't find it to be really cool and very useful, it's okay. You still have to deal with it. And if you haven't been paying attention up to this point, you may want to pay attention now, because you will be faced with this on your exercises, on your review, and on your next test. And people find this to be difficult, so pay attention and see how it works. What's going on here that we're in this problem is we are going to find a formula. Listen carefully, because this is kind of cool. This is what I find cool. We're going to find a formula for converting the volume of something large, something big like this pyramid here. It's pretty big. I mean, it's got feet on the side, so it's a pretty large pyramid. The volume of it is how much sand you can pour in there or water, right? You're talking about volume, you know what I'm saying? And if the dimensions that you have to work with are given in feet or in yards, there's a way to convert it to feet, square feet, cubic feet, as opposed to cubic yards, with a transformation. Like I said, I think it's cool. If you don't fully understand what's going on as far as the geometry goes, you better at least be able to follow the algebra. So here goes. Here's what we're doing. It says, the function v of x equals 1/3 x cubed minus x squared. I'm going to write that down. V, the reason V is because they're talking about volume. And the volume of this particular pyramid is not going to be x times x times x minus 3, although that is what it turns out to be. It's the base area times the height divided by a third, or multiplied by a third. If you don't follow that geometry, it's okay. They're giving you a formula. 1/3 x cubed minus x squared. You will not have to come up with that on your own by trying to remember your geometry that you've all forgotten. You won't have to do that. They'll give you that. This is the volume formula for that pyramid you're seeing on the left. In cubic feet. This is where the beauty of this comes in. This is in feet cubed. If you plug in number of feet on the edge here for the x here and here, then the answer you get by manipulating this, the number that pops out will be measured in cubic feet. But here comes. The function w. Why w? Because you can't use v twice, that's all. This is still a volume formula. Is equal to v of 3x. You understand that because this is happening inside, we really mean 1/3?
Oh, okay, that makes more sense.
Yeah, now it makes more sense, right? Because of the 3 to 1, I mean, the conversion factor for feet to yards is 3 to 1. And so you're thinking, but you're making it 3 times bigger and you're going to yards, it should be 3 times smaller. It is, because this is horizontal. 3 times smaller than what these measurements would be. Every 3 feet is a yard, so you should have 1/3 the number of yards, right? But that's a horizontal, so it should be correct. Just try to go with me on this. Represents the volume in cubic feet when X is measured in yards. So when we measure the dimensions of the thing in yards, this formula here will still pop out in cubic feet. So I may tell you that this pyramid is 10 yards on a side, 10 yards this way, and 7 yards tall. If you plug it into W, your volume will come out in cubic feet instead of cubic yards, which is cool. I find that cool. So here's what we're tasked to do. It says, write a rule for W, and then find and interpret W of 10. So the rule for W is going to be this transformation of V. In other words, this stuff in here replaces all of the X's in V, because we're doing V of 3X. So this W of X right here is equal to V, which is up here with all of its X's replaced with 3X. So we get 1/3 times 3X, all of that inside, cubed, minus 3X squared. Does everybody understand what I wrote there and why? If not, I need to talk to you about it. It's a replacement for X's. So you put it in parentheses, you do the same thing to this replacement as you did to X up here. Here's your 1/3. X gets replaced with 3X. And that X gets replaced with 3X. We're cubing this one and squaring that one. You okay with this?
Yep.
Now we do the math. 1/3 is uninvolved because we got to handle exponents first. So this will be 1/3. What's 3 cubed?
27.
Good. X cubed is X cubed. What's 3 squared? 9. And X squared is X squared. Do you follow what I've got so far?
Yeah.
Now I take 1/3 of 27. What's that? 9. 1/3. 27 divided by 3 is 9?
Yeah.
X cubed, because I'm taking 3 times 1/3 of 27, and then minus 9X squared. This is W of X, after doing the math on it. But what you have here is this. Pay very close attention to this. It's saying that if your X values are measured in yards, plugging it into this will kick out a result measured in cubic feet. That's pretty cool. So what we do is to find W of 10 and interpret the results. That means when you find W of 10, now that we've got a W function, it means to replace all of its X's now that it's been cleaned up with a 10. I get 9 times 10 cubed minus 9 times 10 squared. What's 10 cubed? Gotta do that first. What's 10 cubed? You know that.
1,000.
1,000 times 9?
9,000.
Good. What's 10 squared? 100 times 9? What's 9,000 minus 900?
8,100.
Good. 8,100. 8,100 what?
Feet. Cubic
Cubic feet. Even though the amount we put in was in yards, because this conversion right here allows you to measure dimensions in yards, would kick out your value in cubic feet. And so when you go to interpret this, if you had to write a sentence for what you had, you would say, if the edges of the pyramid were 10 yards and 7 yards, the edges were 10 yards and the height was 7 yards. You see where I'm getting the 7 from? Look at the pyramid. If the edges along the bottom were 10 yards, and I know they have feet there, but we've already done the conversion. These are in yards. The measurements are in yards. If the edges of the pyramid were 10 yards each, and the height of the pyramid were 7, do you see where I'm getting the 7?
I don't.
10 minus 3.
Oh, yeah.
Okay. So we say, this is how we interpret what we have. You got to really understand your formula. And you say this. If the bottom edges were 10 feet and the height of it were, not feet, 10 yards and the height were 7 yards, the volume would be 8,100 cubic feet. Even though your measurements were in yards, the volume comes out in cubic feet because of this. But you have to handle algebraically this way. You follow that at all? This is the transformation. You have to make this transformation by plugging in the x's and v with 3x. That's what we did here. Cleaned it all up, got to here. And now this formula right here has this in yards and the result in cubic feet. That's how you have to interpret it. Okay, I hope you're able to do that. You're going to have one like this to do on the exercises. I hope you go back, look at this, try to think about what we learned, and give it a shot. Okay, so this is the assignment. We're all done. The assignment, if you're doing it on paper, is, are you ready to write?
Go.
All set? So call it 4.7. This is 1 through 7 odd, 8 through 11, 13 to 27 odd. 16 problems. Won't kill you. I think you'll be okay. Okay, there's the end of that one, folks. Hope you're able to see everything. Bye.